In this lecture, we start looking at sampling and the concept of a sampling distribution. We'll start off by defining what we mean by a random sample. Let x1, x2, and so forth up to x sub n denote a collection of random variables with joint PDF given by lowercase g, and notice that this is a function of the values taken on by the n variables, and there's a parameter theta which is possibly multidimensional. Now for each I going from 1 to n, denote the marginal PDF of x sub I by f sub I. So we consider the random variables as resulting from some random experiment. So we have the marginal PDFs denoted by f sub I going from 1 to n. We have the joint PDF denoted by lowercase g. And for each of the marginal PDFs and also for the joint PDF, there is associated with those distributions a parameter, which again is possibly multidimensional. Now, if the random variables x1 through x sub n are mutually independent and identically distributed, we abbreviate that by IID, so independent and identically distributed, so that each has the same PDF, the same marginal PDF, then they are said to constitute a random sample from the distribution with the common PDF, lowercase f. So the initial notation allows for the PDFs of the n random variables to differ. F1 being the marginal PDF of x1, F2 being the marginal PDF of x2, and so forth, up to F sub n being the marginal PDF of x sub n. But there will be some situations in which the marginal PDFs are all the same, and when they are all the same, we can dispense with the subscript. We won't need that, and so in that kind of a situation, the x sub i's, x1 through x sub n, all have the same marginal PDF, which we're denoting down here by lowercase f without a subscript. And so when the random experiment is conducted in such a way that the random variables x1 through x sub n are, again, mutually independent and identically distributed, and again, what that means is they all have the same marginal PDF, then this collection of random variables is called a random sample. So that's what's meant when we say that we've got a random sample of size n. We have a collection of random variables of size n that are mutually independent and identically distributed. Now let x1 through xn be a random sample from the distribution that has common marginal PDF, lowercase f. Okay, so here we're starting off by saying that this collection of random variables is a random sample. And so by that, we can conclude that they are mutually independent and identically distributed. They all have the same underlying PDF. Then, if in this situation, the joint PDF can be obtained from the marginal PDFs in the following way. The joint PDF is equal to the product of the marginal PDFs, and this is by independence. So this first equality follows from the fact that the random variables are mutually stochastically independent. And so if you go back and look at the definition of stochastic independence, the definition was that two random variables are stochastically independent if and only if their joint PDF can be written as the product of the marginal PDFs. And we also said at that time that that definition can be extended to more than two random variables. And so here we're applying that definition, an extension of that definition to these n random variables which are independent. And so by that result, the joint PDF, which again we're denoting by lowercase g, the joint PDF of the random variables would be given by the product of the marginal PDFs, which In general, again, the marginal PDF of the ith random variable x sub I would be f sub I. But then because these random variables are identically distributed as well, again, each of these marginal PDFs, f sub I, are equal to f, this common PDF. And so in this situation, when we're dealing with a random sample, the joint PDF is equal to the product of the marginal PDFs, and each of those is the same. It comes from the same distribution. Now, okay, why are we looking at this? Well, this is important because in many situations, independence can be inferred from the way in which the experiment is conducted. It depends on the way that the experiment's conducted, and experiments can be performed in such a way that the random variables, the measurements that are obtained, are independent from one experimental unit to another. And so when this is the case, we can determine the form of the joint distribution of the sample values by this result. Now, on the other hand, if an experiment is not conducted in a way that guarantees independence, then it can be very difficult, if not impossible, to determine the form of the joint distribution of the sample variables. So if the experiment is done in such a way that the random variables are not independent, then we can't even assert this. All right? So in that kind of a situation, it's going to be very difficult, if not impossible, to determine the functional form of the joint PDF, which we're going to need in order to move forward. Right? It's very important that we have the form of the joint PDF. For example, if we want to perform maximum likelihood estimation, if we want to perform likelihood ratio tests and things like that, we have to be able to construct the likelihood function, and the likelihood function is obtained from the joint PDF. So if we cannot form the joint PDF, if we're not able to even determine its functional form, then we really can't go any further. So that's why it's so important that experiments be conducted in such a way that observations from different experimental units are independent. Okay, now let's talk about what we mean by a statistic. So let x1, x2, and so forth be up to x sub n be a random sample from a distribution, and let's let t be some function of the sample. Since t is a function of the random variables, it is itself a random variable, and if the function t, if the calculation of the function t does not depend on any unknown parameters, then t is called a statistic. So this is the defining characteristic. All right, we've got a sample, we've got a random sample. This definition would actually apply to any collection of random variables, but we're going to be focusing on random samples. But we've got a collection of random variables, and we're going to compute some statistic from those. We're going to compute. We've got a function defined on those random variables. If the calculation of that function depends on any unknown parameters, then that function is not a statistic. But if the calculation of that function does not depend on any unknown parameters, then we call that function a statistic. And so note that all statistics are random variables because they're computed from one or more random variables, but not all random variables are statistics. So we're going to see some examples of this. So for example, let x1 through xn be a random sample from a normal distribution that has a mean of mu and a variance of sigma squared. And let's assume here that both mu and sigma squared are unknown. Okay, so those are unknown parameters. We have a random sample from a normal distribution, but we don't know the mean or the variance of that normal distribution. Now, let's, for starters, as a very simple example, compute a function or define a function on the random sample by returning the first value that we got. Now, this is not necessarily the smallest, it's just the first in the sequence that we've collected. So this function t which is a function of the n random variables, is equal to x sub 1. Well, calculating this function of the random sample does not depend on any unknown parameters, and so therefore this function t is a statistic, again because it does not depend on either of the unknown parameters mu or sigma squared in terms of the calculation of that function. Now, I would point out that since t, which is x sub 1, has this normal distribution, its distribution does depend on the parameters mu and sigma squared. The distribution of this statistic or of this function depends on the one or more unknown parameters, but its calculation does not, and that's the key issue here. Does the calculation of this function of the random variables depend on any unknown parameters? If not, then the function is in fact a statistic. Now let's consider another example. Let's let the statistic t, which again is a function of the sample, be equal to x1, the first obtained value, minus mu, which is unknown. Well, since the calculation of this statistic depends on an unknown parameter, then while this is a random variable, it's a function of the random sample and therefore a random variable, but it's not a statistic, okay, because its calculation depends on the unknown parameter mu. Now, in this case, the distribution of the random variable t has a normal distribution with a mean of 0 and a variance of sigma squared. So again, its distribution does depend on at least one of the unknown parameters, but again, that really is not relevant to whether or not this is a statistic or not. The relevant point is whether the calculation of this function of the random sample depends on at least one unknown parameter. And then finally, let's consider the random variable t given by this expression, so x1 minus mu over sigma. Because the calculation of this function of the random sample depends on at least one of the two unknown parameters, again, it's not a statistic. Now, in this particular situation, the distribution of t is normal with a mean of 0 and a variance of 1, and therefore a standard deviation of 1. So the distribution of this statistic does not depend at all on any unknown parameters. But again, for the purposes of determining whether this is a statistic, the relevant point is whether its calculation depends on at least one of the unknown parameters. Okay, now let's talk about sampling distributions, and in particular the sampling distribution of a statistic. Since a statistic is a random variable, it has a probability distribution. That probability distribution is also called the statistic's sampling distribution, to emphasize the fact that it is the distribution of a random variable computed from a sample. So sampling distribution is just kind of a fancy word or a fancy term for a probability distribution, but in particular the probability distribution of a sample statistic. Now, inferences about a population, which is what we're all about in statistics, right? That's the goal, to make inferences about populations. So inferences about a population are based on one or more statistics computed from a random sample selected from that population. Now, in order to make inferences about a population using a statistic, we need to understand how that statistic behaves. And that behavior is contained in the statistics sampling distribution. And in particular, the probabilistic behavior of the statistic is contained or encapsulated within that statistics sampling distribution. So knowledge about a statistics sampling distribution is necessary in order to use it to make inferences about a population. So if you think back to your first methods class, and also at the beginning of this course when we talked about, when we gave an overview of what statistics is all about, remember that the big idea here is that we want to be able to answer questions about populations of interest. But we're not able to look at the entire population for a variety of reasons. And so because of that, what we do is we obtain a sample from the population of interest. We study the sample by calculating one or more descriptive statistics, summary statistics, sample statistics, and now we know the definition of a statistic, don't we? But we analyze that sample by calculating one or more statistics, and then we use what we've learned about the sample, and we turn around and we generalize that in a rational, valid way to the population. And then we answer questions about the population in that process. And so the question is, it's what we're doing here is we're going from the specific data that we've observed and generalizing that to the population from which that sample was obtained. And so the question is, why? How can we do that? I mean, what gives that process its validity? How can we even begin to develop procedures that allow us to do this? And this is what we're talking about here. We're using one or more sample statistics in order to make inferences about the population from which the sample was obtained. In order to do that, we have to know something about the probabilistic behavior of those statistics. And that probabilistic behavior is contained in the sampling distributions of those statistics. And so this really provides the foundation for statistical inference. And certainly for the rest of the course, what we'll be doing in this course, that this provides the foundation for that. But really, the idea of a sampling distribution provides the foundation for all of inferential statistics. And because a sampling distribution is a probability distribution, if you were wondering why we were spending so much time on probability and distribution theory, this is why. Because we have to have that mathematical probabilistic knowledge. We have to have that framework, the terminology, the concepts, the notation, in order to understand what a sampling distribution is and to be able to derive sampling distributions and do calculations with them. So everything that we've done up to this point in the course with respect to probability and distribution theory has been laying the groundwork for this discussion, this coverage of sampling distributions, which again provides the foundation for all of inferential statistics. So we can think of sampling distributions as being a link. Sampling distributions along with the probability and distribution theory, all of that provides the link between descriptive statistics, which if you think back to your first methods course, that's what you would have covered first in that course. So sampling distributions, which rests upon probability and distribution theory, provides the bridge between those descriptive statistic techniques and the inferential techniques that you would have learned in the last part of your first methods course. So this is a very important topic, and I would say that if one does not understand the concept of a sampling distribution, then statistics is really not going to make sense. You really do need to have at least a basic understanding of what a sampling distribution is and how and why it's used. All right, so continuing on here, talking about sampling distributions of a statistic. And again, the sampling distribution of a statistic is just the probability distribution for that statistic. So we're going to be interested in understanding certain things about the sampling distribution of a statistic. In particular, we're going to be interested in the mean of its sampling distribution, the variance of its sampling distribution, and also the standard deviation of its sampling distribution, which is oftentimes abbreviated and called the standard error of the statistic. So in other words, when we talk about the standard error of a statistic, what we're talking about is the standard deviation of the sampling distribution of that statistic. We're also going to be interested in the shape of its sampling distribution, whether it's symmetric, or if not, if it's skewed, and if it's skewed, is it left skewed or right skewed? We're also interested in the heaviness of the tails of the sampling distribution of a statistic. And if we can determine it, we would like to know the probability density function of the sampling distribution of a statistic. And then finally, we'll be interested in understanding the various characteristics of the sampling distribution when we have large samples. Now, in many cases, in fact, in most cases, it's going to be impossible to determine the actual form of the sampling distribution of a statistic. Now, in such situations, we'll be interested in determining whether suitable approximations to the actual distribution exist, and if so, to find those approximations. So let's look at the sampling distribution of the sample mean as a very important application of the concept of a sampling distribution. So let x1 through xn denote a random sample from a distribution that has a mean of mu and a variance of sigma squared, and let x bar denote the sample mean. So let me just stop here and just reiterate that we have a random sample of size n, x1, x2, and so forth up to x sub n. By calling this collection of random variables a random sample, what we're implying here is that the random variables are mutually stochastically independent and they are identically distributed. They all come from the same distribution. We're also saying here that the distribution from which the sample is obtained has a mean of mu and a variance of sigma squared. Okay. Now, since x bar, the calculation of the sample mean, does not depend functionally on any unknown parameters in its calculation, it is a statistic. The sample mean is a statistic. In order to use x bar, the sample mean, to make inferences about a population, we'll need to know something about how it behaves. This behavior is contained in its sampling distribution. And here are some of the things we would like to know. What is the mean of the sampling distribution of x bar? In other words, what is the mean of the sampling distribution of the sample mean? What is the variance of the sampling distribution of the sample mean? What is the PDF? Can we find the PDF of the sampling distribution of the sample mean? Now, we can answer some of these questions analytically and very generally. It can be shown that the mean and variance of the sampling distribution of the sample mean are given by the following. So I'm using this notation here that I'm pointing to in slide 9, the lowercase Greek letter mu with an x bar in the subscript to denote the mean of the sampling distribution of the sample mean. So the mean of the sampling distribution of the sample mean. And it turns out that that is equal to mu, which, again, remember from the previous slide, that is the mean of the population from which the sample has been obtained. And so this is saying that the mean of the sampling distribution of the sample mean, the mean of the probability distribution of the sample mean, is equal to mu, the mean of the population that we're sampling from. Likewise, the variance, and this is the notation that I'm using here, the variance of the sampling distribution of the sample mean is equal to, in this framework where we have a random sample of size n, the variance of the sampling distribution of the sample mean is equal to sigma squared over n, where sigma squared is the variance of the population we're sampling from, and lowercase n is the sample size. Now the proofs of these are very straightforward, and you've got them in the notes there. So denote the mean of the sampling distribution of the sample mean by mu sub x bar, as we've already stated. Okay, another way to write that would be the expected value of x bar. Well, x bar, the sample mean, is just 1 over n times the sum, I going from 1 to n, of the x's. And so I can replace x bar by that expression. Now I'm going to use properties of the expectation operator, and in particular the linearity property of the expectation operator. I can pull the 1 over n outside of the expectation, and then I've got, and I'm combining several steps here. I would pull the 1 over n out, then I would have the expected value of the sum of the random variables. And I can, because of the linearity property of the expectation operator, the expectation of a sum would be the sum of the expectations. Okay? And so I've combined two steps there, but that's how we get there. We're just using the linearity property of the expectation operator. And so the mean of the sampling distribution of x bar, so far we get down to this point, is equal to 1 over n times the sum, I going from 1 to n, of the expected values of each of the random variables. But because the random variables are identically distributed, they all come from the same distribution, and that distribution has a mean of mu. So each of these expected values, it's hard for me to highlight this here, but each of these expected values is mu, and so we're adding mu up n times, so that would be n times mu, but then out front we have a 1 over n, so that is just mu. So what this tells us is that the mean of the sampling distribution of the sample mean is always going to be equal to the mean of the population that we're sampling from. And so that's what we're saying here in this slide. The mean of the sampling distribution of the mean of a random sample is equal to the mean of the distribution from which the sample was obtained. And this is true for any distribution with finite mean. So that's kind of an amazing thing, or at least it may seem so, that regardless of the distribution you're sampling from, if you have a random sample from that population and you calculate the sample mean, then although the sample mean is a random variable and varies from one sample to another, and any particular realization of the sample mean will more than likely not be equal to the population mean, we know that the mean of its sampling distribution, in other words, the mean of the probability distribution of the sample mean, is always equal to, exactly equal to the mean of the population that we're sampling from. Now, denote the variance of the sampling distribution of the sample mean by sigma squared sub x bar. So again, the variance of the sampling distribution of x bar. Then by definition, or just another way of denoting this, the variance of x bar. This is the variance of 1 over n times the sum of the x's. And so then I can use properties of variance and expectation, all right, that we've seen before. If I want to pull the constant out, the 1 over n out, I've got to square that. And then you'll remember, based on the properties of covariance, when we've got uncorrelated random variables, then the variance of a sum is equal to the sum of the variances. Now, because, and you'll also remember when we defined and talked about independence, independent random variables are uncorrelated, all right? And so because of that, the variance of the sum is equal to the sum of the variances. Now, because the random variables are identically distributed, they all have the same variance, which is sigma squared. And so this results in the variance of the sampling distribution of the sample mean being equal to sigma squared over n, where sigma squared is the variance of the underlying population and n is the sample size. So therefore, the mean of the sampling distribution of the mean of a random sample is equal to the mean of the distribution from which the sample was obtained. And this is true for any distribution with finite mean. In addition, the variance of the sampling distribution of the mean of a random sample is equal to the variance of the distribution from which the sample was obtained divided by the sample size. And again, this result is true for any distribution as long as that distribution has a finite variance, which is going to be all the distributions that we would look at in this course. Now, the standard error of the sample mean, which you'll remember, the standard error of a statistic is the standard deviation of its sampling distribution. And so the standard error of the sample mean is equal to the square root of its variance. And so the standard error of the sample mean is equal to sigma over the square root of n, where sigma is the standard deviation of the population we're sampling from, and n, again, is the sample size. Now, note that because we have n in the denominator in both the formula for the variance of the sampling distribution of the sample mean, as well as the standard error. As n increases, as n goes to infinity, the variance of the sampling distribution of the sample mean converges to 0, and therefore also does the standard error. And so as the sample size increases, the variability associated with the sample mean decreases. And this is one of the reasons, not the only reason, but one of the reasons that we use the sample mean to make inferences about the population mean. Because as we increase the sample size, the variability associated with the sample mean increases. The variability decreases, and therefore the reliability associated with that sample mean increases. So again, as the sample size increases, the variability associated with the sample mean decreases, and therefore it becomes a much more reliable estimator of the population mean as the sample size increases. The other reason that we use the sample mean to make inferences about the population mean is because of this fact here. The mean of the sampling distribution of the sample mean is always equal to the population mean itself. And so this means that the sampling distribution of the sample mean is always centered on the population mean, in the sense that, remember that the mean can be thought of as the center of mass of a distribution. And so the center of mass of the sampling distribution of the sample mean is always equal to the mean of the population from which the sample was obtained. So we've identified two very important results, two very important characteristics of the sampling distribution of the sample mean, and these are very important results. We now know that when we're sampling from any distribution, as long as that distribution has a finite mean and variance, then we now know that the mean of the sampling distribution of the sample mean will be equal to the mean of the population we're sampling from, and the variance of the sampling distribution of the sample mean will be equal to the variance of the population we're sampling from divided by the sample size. So those are two very important results to know. But now another question would be, could we determine the actual PDF of the sampling distribution of the sample mean? So what about finding a complete specification of the sampling distribution of the sample mean? For example, can we find its PDF and its CDF? Now, this is a much more difficult problem in general because the actual distribution of the sample mean depends on the distribution from which the random sample was obtained. So, it depends on whether we're sampling from a normal distribution or a binomial distribution or a gamma distribution, an exponential distribution. All of those distributions that we've looked at, and an infinite number of other distributions that we haven't looked at, perhaps that we don't even have any mathematical representation for. The actual PDF of the sampling distribution of the sample mean will depend on the distribution that we happen to be sampling from, and in a real-world problem, in a real-world situation, we're not going to know what the distribution, what the actual population or distribution is that we happen to be sampling from. So that's one problem. If we don't know the underlying population, the underlying PDF of the distribution we're sampling from, then we're not going to be able to derive exactly the sampling or the PDF of the sampling distribution of the sample mean. But even if we did know the distribution from which we were sampling, finding the exact sampling distribution of the sample mean, and in particular finding its PDF or PMF, can be very difficult mathematically. So for those two reasons, we're in most cases in the real world, we're not going to be able to know, or we're not going to be able to derive the actual PDF or the PDF of the actual sampling distribution of the sample mean. But now there is one interesting situation where we can. Now there are other situations where we could, and we'll see some examples of those, but one interesting situation is when we're sampling from a normal distribution. So suppose that x1 through xn are a random sample from a normal distribution with mean mu and variance sigma squared. And let x bar be the mean of that sample. So x bar is the mean of a random sample from a normal distribution with mean mu and variance sigma squared. Then in that case, it can be shown that the sample mean also has a normal distribution. And so we would know in that kind of a situation that x bar is itself normally distributed with a mean equal to mu sub x bar and a variance equal to sigma squared sub x bar, where again, we know that this would be the case in this situation because it's always going to be true that the mean of the sampling distribution of x bar would be equal to the mean of the population we're sampling from, mu, and the variance of the sampling distribution of x bar would be equal to the variance of the population we're sampling from divided by the sample size. So the new result in this slide is that if we are sampling from a normal distribution, then we know, it can be shown, it can be proven, and we may do that in a subsequent lecture video. It can be shown that the sample mean is also normally distributed. Now, in most situations encountered in practice, the actual distribution from which we are sampling is not exactly normal. Some distributions may be similar to the normal distribution, while others are not even close. For example, if they're highly skewed or have higher kurtosis. What can we do in those situations? Well, the next result proves very helpful in this regard, and this is arguably one of the most important results in probability and statistics. This result is called the central limit theorem, and it states that regardless of the distribution from which we're sampling, as long as the distribution has finite variance, then for sufficiently large samples, the sample mean is approximately normally distributed. So this is a result that you would have seen in your first methods class. We're going to look at this result, the central limit theorem, in a bit more detail than you would in that first methods class. So let x bar be the mean of a random sample from a distribution with finite mean mu and finite sigma squared, finite variance sigma squared. Then let's define a new random variable we'll call z sub n to be the standardized version of x bar. So we're going to take x bar and from it subtract the mean of its sampling distribution, mu sub x bar, and divide the difference by the standard error of x bar, which is the standard deviation of its sampling distribution. And so expressed in terms of what these values are equal to, z sub n is equal to the sample mean minus mu, the mean of the population we're sampling from, divided by sigma over the square root of the sample size. So this is a random variable. It has a probability distribution. That probability distribution is called its sampling distribution. And so let's denote the sampling distribution of z sub n by, let's say, h sub n. Then the central limit theorem tells us that at each value of z, as long as z is a point of continuity of the underlying distribution, then as n increases, as n goes to infinity, this sequence of CDFs evaluated at z will converge to a value equal to the CDF. This is cap phi evaluated at the same value of z, and this is the CDF of the standard normal distribution. So what we have here, what we're doing, let's think carefully about what this represents. We've picked a value, we've picked a real number z on the number line, and we're considering evaluating the CDF of z sub n at that value of z, and doing so for sample sizes that are increasing without bound. And so that generates a sequence of real numbers. And what this is saying is that sequence will converge to the value of the CDF of the standard normal distribution evaluated at that same value of z. So in other words, the sampling distribution of Zn becomes more and more like the standard normal distribution as the sample size n gets large. And so for large samples, the sampling distribution of Z sub n can be approximated by the standard normal distribution. Now, that is a more detailed and a bit more formal explanation and representation of what the central limit theorem is telling us. So, and again, for large samples, the sampling distribution of this standardized version of x bar, Z sub n, can be approximated by the standard normal distribution. And we express this by saying that for sufficiently large samples, right, for sufficiently large samples, Z sub n, which again is this standardized version of x bar, is approximately standard normal. So well, I've got my tilde here, but I've got a dot on top of that, all right, and that what that means is it's approximately distributed as. And so what this is telling us is that for sufficiently large samples, while we may not know the true sampling distribution of Z sub n, we can approximate that sampling distribution by the standard normal distribution. And so it follows that for large samples, the sampling distribution of the sample mean itself, x bar, is also approximately normally distributed. And we know the mean and the variance of that sampling distribution. We know, because this is true for all distributions that we happen to be sampling from, the mean of the sampling distribution of the sample mean is mu, the mean of the population we're sampling from, and the variance of the sampling distribution of the sample mean is equal to the variance of the population we're sampling from divided by the sample size. And so the result of the central limit theorem here tells us that x bar itself will be approximately normally distributed, all right, for or when n is large, when the sample size is large. And in general, the quality of the approximation improves as the sample size gets larger and larger. Now, before we move on, what I'd like to do is look at a very simple example that demonstrates the idea of a sampling distribution. I like to show this in several of my courses where we cover sampling distributions. And I think it really helps solidify the idea of what a sampling distribution is. So what I want to do is I want to look at this very, very, very simple population. The population that contains the values 1, 2, and 3. So this example is probably the simplest example that one could come up with to talk about the idea of a sampling distribution. But I think it does, I think it's effective in helping us to understand what a sampling distribution is. So what we want to do first is think about this population of 3 values. And we can calculate the mean and the variance of this population. The mean of this population would be 1 over n. Cap n is 3 here. So 1 over cap n times the sum of the x's, the values in that population. And so when we calculate this, we get a population mean of 2. The variance for this finite population is given by this expression here. Remember that the variance is the average squared deviation about the sample, about the population mean in this case. And so we would have 1 over cap n times the sum, I going from 1 to cap n, of x sub I minus mu quantity squared. Now, mu is equal to 2, and so we have 1/3 times this sum, the sum of squared values, 1 minus 2 quantity squared, plus 2 minus 2 quantity squared, plus 3 minus 2 quantity squared. And so we see here that the variance of this distribution, of this population, is equal to 2/3. So the mean is 2, and the variance is 2/3. The standard deviation of this population is therefore the square root of 2/3. And so now what I want us to do is think about the process of sampling from this population random samples of size 2, okay, and I want to think about the sampling distribution of the sample mean. So let me see here. We can think about having, let's say we get 3 slips of paper, and on each slip of paper, on one slip we put 1, on another slip of paper we write 2, and on the third one we write 3. And we put these slips of paper into a hat, and we shake it up, and we select what we do is we select a random sample of size 2 from this population. And so what that means in this context, because in order to be a random sample from this finite population, the observations have to be identically distributed, and they also have to be stochastically independent. So in order for them to be stochastically independent, we have to select a piece of paper, but then we have to put it back in. So what we're going to do is reach into the hat without looking, select out a piece of paper, note the number, write it down, put the slip of paper back in the hat so that it could possibly be selected again. Mix up the hat, mix up the slips of paper in the hat, and then again draw the slip out of paper again. We do that twice. Okay, we're sampling with replacement, sampling at random and with replacement. And then what we're going to do is we're going to calculate the sample mean for the sample that we obtain. Now, here is a schematic of what I'm talking about. And so we have our population up here containing 3 values. The mean of this population is 2. The variance is 2/3. And we see here, and if you think about it, and you could use your counting techniques to determine this, but there are 9 possible random samples taken with replacement from this population of 3 values. And so we could get a 1 on the first draw, a 1 on the second draw, a 1 on the first draw, a 2 on the second draw. We could get a 1 on the first draw and a 3 on the second draw. We could get a 2 on the first draw, a 1 on the second draw, a 2 on both draws, a 2 on the first draw, a 3 on the second draw. Or we could get a 3 on the first draw, a 1 on the second draw, a 3 on the first draw, a 2 on the second draw, or a 3 on the first draw, and a 3 on the second draw. So there are 9 possible samples possible. There are 9 possible ways that this experiment of selecting a sample at random and with replacement from this population, 9 elementary events in the sample space of that experiment. Now, we're going to define a random variable on the sample space of that experiment. In particular, we're going to be focusing on the sample mean. And so for this first sample, the sample mean is obviously 1. For the second sample, the sample mean is equal to 3/2. For the third sample I've got listed here, the sample mean is 2. For the fourth sample possible here, the sample mean is 3/2, and so forth. We see that for this sample, the sample mean is 2. For this sample, the sample mean is 5/2. For this sample, the sample mean is 2. For this sample, the sample mean is 5/2. And then finally, for this sample, the sample mean is 3. So we have defined a random variable on the sample space of this underlying experiment. And let me just say that because we are sampling at random and without replacement, by virtue of how we're doing this experiment, these elementary events are all equally likely. Okay? And so to compute probabilities involving these elementary events, all we would have to do is count the number of elementary events comprising an event of interest and divide by the total number of outcomes, which in this case is 9. Now, we see here the possible values that X bar can take on for this experiment. It can take on the value 1, 3/2, 2, 5/2, and 3. And so those 5 values comprise the sample space of the random variable X. The probabilities associated with those values, in other words, the values of the PMF for each of those values are listed here in this second column. So the probability that we get a sample mean equal to 1 is 1/9. The probability that we get a sample whose sample mean is 3/2 is 2/9, because again, there are two samples, here and here, where that sample mean is 3/2. The probability that we get a hold of a sample whose mean is 2 is 3/9, because there are three possible samples where three samples where the sample mean is equal to 2. The probability that the sample mean, or that we get a hold of a sample whose sample mean is 5/2 is 2/9. And then finally, the probability that we get a hold of a sample whose mean is 3 is 1/9. So this is the PMF of the distribution of X bar for this experiment, for this situation where we're selecting selecting random samples of size 2 at random and with replacement from this population of 3 values. So this is the PMF of the distribution of X bar. It is therefore its sampling distribution. Now we want to compute the mean and the variance of this sampling distribution as well as the standard deviation. All right, and so we do that using the techniques that we've learned how to use in this course up to this point. So again, I've got a column here where I've got X bar times the probability that the random variable X bar takes on that value. And so I'm just multiplying corresponding entries in these first two columns. And so this value down here would, the column total for that column would give us the expected value of X bar. This column would give us the expected value of X squared, because it contains the values which are the square of the values in the first column times the corresponding probability. Okay, and so we have here the mean of the sampling distribution of X bar, which is the expected value of X bar, another way to write that, is equal to 2. The expected value of X bar squared turns out to be 156/36. Again, that's the column total for this fourth column. And so using the expansion formula for the variance, we get the variance of sigma squared. I'm sorry, the variance of the sampling distribution of X bar, which is can also be written here as the variance of X bar. Turns out to be 1/3. So, and then once we have that, then we know that the standard deviation of the sampling distribution of X bar, or in other words, the standard error of X bar, would be the square root of 1/3. Now, I just want to point out that in this example, the mean of the sampling distribution of X bar, which is denoted mu sub X bar, is in fact equal to the mean of the population or distribution that we sample it from, because the mean of the sampling distribution of X bar was shown to be 2, and that is the mean of the underlying population. And also, the variance of the sampling distribution of X bar, which is 1/3, is equal to the variance of the population we're sampling from divided by the sample size. What is the variance of the underlying population? It's 2/3. What is the sample size? It's 2. So 2/3 over 2 is 1/3, and that is the variance of the sampling distribution of X bar. So this demonstrates, it doesn't prove, but it demonstrates the fact of what we said way back here on slide 9, that when we're sampling, collecting or selecting a random sample from a population with mean mu and variance sigma squared, then it will always be the case, not just in special cases, but it will always be the case, that the mean of the sampling distribution of X bar is equal to the mean of the population we're sampling from, and the variance of the variance of the sampling distribution of the sample mean will always be equal to the variance of the population we're sampling from divided by the sample size. So that is where we're going to, I'm going to end up or finish on this lecture video. There's some additional material that I'm going to create a lecture video for to augment the lecture notes, and I'll post that as well. And then we'll get back into the rest of the notes from this particular module. So this is going to be a very quick module. We can get through this quickly because we've laid a very firm foundation of probability and distribution theory. And this is just an application of those kind of ideas.